Okay, this video is going to be about calculating the pH of a weak acid, okay? So the difference between a strong acid and a weak acid, a strong acid completely dissociates where a weak acid only partially dissociates, okay? So with that being said, we can't use the starting concentration of the weak acid to figure out the pH of the acid, okay? Fortunately for us, this will look very similar to solving for Kc or solving for an X within an equilibrium expression. Okay, so because we're going to do the same thing. We're going to be using Rice tables, we're going to be using initial concentrations, and we're going to be using mole ratios from a balanced chemical equation. Okay, so if we just take a gander at one of these examples, because there's something that's within these notes that we're going to be able to do to make these problems 10 times easier. Okay, so the question says calculate the pH of a 1 times 10 to the negative 4 molar solution of acidic acid. Okay, and acidic acid is CH3COOH, okay? And then it gives us the Ka, which is 1.8 times 10 to the negative 5th. And most of the time, Kas can be looked up in a table or a book, or you can search them on the internet. Okay, so the first thing you have to do is start with a dissociation equation for the weak acid that we're talking about. So if it is a weak acid that only has one proton, then that proton will dissociate off, and then what will be left is the anion. So in this case, you have acidic acid, which, or you can think about it how I wrote it, which is CH3COOH, and it will be in equilibrium with the H plus and the CH3COO minus, which is the acetate ion. Okay, and then we just set up a Rice table. So the first thing is our reaction. The next thing is what do we initially have? Well, before the reaction takes place, we only initially have the concentration of the acidic acid. So our starting concentration for the acidic acid is 1 times 10 to the negative 4th, and then we have 0 proton and then 0 of the acetate ion before the reaction even starts. Okay. The change in, since we don't have any numbers for equilibrium, we're going to say that the change in is an X, okay? Now, lucky for us, in this equation, everything is a 1:1:1 mole ratio. If it wasn't, we would have to put, we would have to use numbers, but in this case, we're just looking at X, so it would be like 1X, okay? So since I'm dissociating the acidic acid, or that's what I'm starting with, then that is going to be minus, where I'm making H plus and the acetate ion, so those will both be plus, okay? Now, if we look here, at equilibrium then, I'm going to take the starting minus what the change was, which was X, and then here I'm adding. Okay. If I write the Ka equation just like we do for any equilibrium problem, this is what it would look like. We would set that equal to the Ka, which was given to us, and what we notice is we have two x's here. We have an x squared, and we have a minus x. Okay, this is where things start to get a little tricky. Usually, you would have to set this whole thing, so you would carry the 1 times 10 to the negative 5th over here, and then it would look sort of like a quadratic formula equation. Okay, but in general chemistry, we like to take things very simply, and we can make the assumption that the X that's being subtracted from the acidic acid is actually so small that it's not going to really affect the starting concentration of the acid. Okay, so what we can actually do is we can say, well, I don't really care that you're there, negative X, but what I'm going to do is, so that I can reset my equation, 1.8 times 10 to the negative 5th is equal to x squared divided by 1 times 10 to the negative 4th. Okay, and then that makes this 10 times easier to solve, and then these problems look just like the equilibrium problems that we did in chapter 15. Okay, if you're interested in why we can neglect that x, you can go ahead and read this guy. It kind of explains it a little bit more for you in depth. And then on the next page, it kind of illustrates how you can take out the x and then solve for x using the square root and then solving for the H plus concentration. Okay, so with that being said, let's go ahead and look at an example here. Okay, Okay, so let's look at an example where we're going to solve the pH of a weak acid, sort of like within our notes, sort of how it is within our notes. Okay, so you can read this. It talks about the hypochlorite ion, which is found in household bleachers and disinfectants. It also has an active ingredient that forms forms when swimming pool is treated with chlorine. Okay, so we're actually looking at the equilibrium of hypochlorous acid, which is there, and it wants us to calculate the pH if the starting concentration that I have is 0.1 molar. Okay, the first thing I'm going to do is set up a chemical equation. So I have hypochlorous acid, which is HOCl3, or Cl, sorry, and it's in equilibrium. So since it's a weak acid, it'll be an equilibrium equation, and there's only one H, so that H will come off. So it'll be H plus and OCl minus. Okay, so that's our chemical equation. And then we're just going to do a RICE. Okay, so initially it tells me that I'm starting with a 0.100 molar of hypochlorous, where I'm starting with 0 and 0 of this guy. Okay, so then the changes, since it's a 1 to 1 to 1, I'm going to be subtracting X, and then I'm going to be adding 2 X's. So then at equilibrium, it's going to be 0.100 minus X, and then this will be X and X. Okay? And then we can set the Ka equation up. So the Ka for hypochlorous acid will be equal to H plus times OCl minus divided by the HOCl concentration. Okay? So if I plug my numbers in, it's going to be X times X divided by that 0.100 minus X, and that's going to be equal to Ka that's given to us, which is 3.5 times 10 to the negative 8th. Okay? Now, to simplify our math here, we're going to get rid of this X. We're going to neglect the minus X, saying that it's too small. It won't really affect the 0.1. And so we're going to get X squared divided by 0.100 is equal to 3.5 times 10 to the negative 8th. And then you can solve for X. So X squared is equal to 3.5 times 10 to the negative 9th. And then I can take the square root of both of these guys. So X is equal to 5.9 times 10 to the negative 5th. But this, you have to remember, is the H plus concentration. The question asked for pH. So then we have to do pH is equal to the negative log of H plus, which is going to be the negative log of 5.9 times 10 to the negative 5th, which turns out to be 4.23. Okay, and that's how you calculate the pH for weak acids. You can also calculate the starting concentration if you're given pH, because then you can solve for H+, plug it into the RICE table, and then go backwards. And we'll look at some examples of that inside class. Thanks, guys.